Okay, here is a video looking at travelling waves, and it's going to be a recap of what we've done previously, some simple wave theory, and then it's going to move on to looking at how we mathematically model a wave. So let's just go with some really basic theory to start with. If we look at a wave, slightly bigger, and let's just recall the basics of what's included in that badly drawn wave. Okay, what do we have first of all? Well, I'm going to look at this with a time axis and then a distance axis. It's quite important actually that distance there and time here, because that sometime is actually drawn as a distance and then you measure wavelength. However, in this instance, that is going to measure the time period. Which is given the symbol t. That's the time for one wavelength to pass. Of course, we have an amplitude as well, which is the maximum displacement. Equals the max displacement. But this is an interesting thing. Actually, let me give that symbol y. The displacement can be anything. Can be any value. It doesn't always just need to be the maximum or the minimum, but you might have a point anywhere along here where you're interested in the displacement. And so this one here, y, I've just placed in there as displacement. So I'll just write y equals displacement at time t. So at time t, there, that is my displacement y. Slightly confusing with the y up there, but I hope you know what I'm after, what I'm getting at here. Right. What do we want to look at next? So we're happy with the time period. The last thing we haven't yet commented on is the frequency. And that is the number of cycles per second, or the number of waves, if you prefer, per second, and it's given the equation 1 over the time period, which is the only equation you really had to learn previously. Get a little bit of basic maths. Let's just say, for instance, that this here is 0.1 of a second. If that's 0.1 of a second, then what's the time period? Well, the time period will be half of that, 0.05 seconds. And what's the frequency? Well, the frequency is going to be 1 over 0.05, which gives us 20 hertz. If this were running at, say, 5 meters and minus 5 meters, then the amplitude would be 5 meters. And I think that really sums up all that you knew about a basic theory about waves. What we're going to try and do now is put some sort of mathematical construct onto that. So here's, let me draw that setup again. Okay. Now, first of all, what we want to do is try and find an expression which will work out the displacement y at any time position. That could be anywhere along this axis, time axis. So we're looking at displacement against time in seconds. How do we go about that? Well, I always think it's quite nice to think about this as a little clock. This clock arm rotates around, and at any given moment, its position next to the horizontal will indicate the displacement of that wave. Of course, that's dependent on the number of angles that it's gone through. Good. I'm sure you're familiar with the idea that this wave looks very similar to a sine wave, where y equals sine of x. And that oscillates from 1 to -1. Good. So, what we're going to do is we are going to, maybe this is actually easier to say sine of theta rather than sine of x, so let's make that into theta. And you're familiar with it. This goes between, let's put on some popular values, 180 degrees, 90 degrees, obviously 0, 270, 360, and then it repeats. 90 degrees in addition to, or we repeat the cycle from there. I'm sure you're happy as well with the concept of radians, in that this is pi over 2 radians, pi radians, 3 pi over 2 radians, and 2 pi radians. Excellent. So what we're trying to do is, as this arrow moves around one full cycle, the different values of theta, of course, reflect different positions of the wave. And this here as well represents different positions along here. However, we're using time rather than angles. So how do we liken the time to angles, and how do we join the two together? Well, let's talk about that. We know that this makes one complete rotation in a time period. We also know that it goes around 360 degrees, or 2 pi radians, in that time. So what we're looking for is the fraction of how many radians we've gone through, how many radians, degrees, how many angles we've gone through as a proportion of the total. Good. Let's write down that fraction. So let's say the number of angles compared to 360 is going to be the same as the time period by the time that you have taken of the entire cycle, so the time period here, compared to the entire cycle. And that's going to give us the number of angles we've gone through compared to 360. So therefore, quick little rearrangement, theta over 360 multiplied by t gives us that time period. So we are now representing a time period in terms of a number of angles which we've gone through. It's also probably neater to give it 2 pi. Oops, sorry, wrong way around. It's probably neater to give it in radians. So we'll say it's theta over 2 pi multiplied by t. Brilliant. And indeed, we could write this as 2 pi over t multiplied by t gives us the number of thetas we're going around, or indeed omega t, where omega shows how fast we are cutting through the angles. So this here, which is omega, shows how fast this is rotating through the angles. Good. So we're trying to bring together this idea of angles to this wave we have here. Good, right, let's add in, obviously, our amplitude, minus A. We've said that this already looks like a sine, but this oscillates between 1 and minus 1. This oscillates between A and minus A. So therefore, the general form of our equation so far, y, is going to equal a sine of an angle, and we can now say that that angle indeed is omega t, and because that would only bounce between 1 and minus 1, if we multiply it by the amplitude, that allows it to bounce between the amplitude and minus the amplitude. So suddenly now we've worked out y, the displacement, at different time periods based upon this idea called omega, where omega is 2 pi over t. Good. The general equation, the general form of our equation. I'm just going to put a little box around that because we're going to give a few examples in a minute, but not before I've talked about one more thing, and that is, here we go. Let's imagine I have my wonderful oscillating sinusoidal wave. Let's drag this along a little bit. T, displacement, and I know that the general form of my equation is A sine omega t. Let's say y at this time could be anything, could be down here. That's y at that time period t, but this is a full time period. Now, here's another wave that looks very similar to the first one. For those of you that are more mathematically minded, you're probably saying to yourself, oh, that's a cosine wave, because it starts at 1, sine starts at 0. And you're right, it is a cosine wave. So we could write the blue one as y equals a cosine omega t, which wouldn't be wrong, that's fine. However, the problem is we just want one general. We're looking for one general expression rather than having to write lots of different expressions. So how does sine and cosine relate to ourselves? Can I rewrite this one in some way to match that? So I suppose what we could say is, actually, this graph here is very similar to that one if we just changed our start point to being there. So if I start from there, suddenly we have the same graph. If I started 3/4 of the way through, then suddenly I can say, oh, it's the same thing. I'm now back to a sine graph. So how do we indicate a shift? And where do I put the shift in this equation in order to make that work? Well, very simply, what I do is I introduce something called a phase difference. A shift of the graph. If it's minus, of course, that indicates a minus indicates a shift to the right, mathematically. If it's a plus, it indicates a shift to the left. That's probably worth writing in actually. Positive equals that type of shift. Negative equals that type of shift. Okay, so YA cos omega t is going to be the same as, let's go write this in here, y equals a sine omega t. Note that this is not changing because the frequencies and the time periods are the same for both of these waves. However, what has changed is minus the shift of 3/4 of a wavelength, 3/4 of a wavelength in radians, gives me that. I could, of course, go the other direction if I wanted, and say a sine omega t plus pi by 2, because in that case, just go back to the blue wave, coming backwards, the shift here is 1/4 of a wave, but this time I'm moving in a positive direction 1/4 of a cycle. Good, let's just try and add another one, just to make life really difficult. What happens if I went from here, same frequency, so now this is just the inverse of the blue. Well, what I could say is saying y equals minus a, minus a cos omega t. Or indeed, I have exactly the same as a sine wave, but now 1/4 of a cycle, not time period, sorry, 1/4 of a time period in the negative direction. So that would be y equals a sine omega t minus pi over 2. Or I could move the other direction, and the other direction would be positive 3 pi over 2. So all of them are the same. Good, okay, so let's just run through that one more time. This is the general form of my equation, up to there. But rather than writing out these different forms of the equation, depending on the different starting points and shapes, it's easier if I still use this general form but introduce this phase difference, which says how much is this one merely a shift of that one? How much is this one merely a shift of that one? I have to use a little bit of a sense of, I'm going to need to guess at how much this is a shift. How far do I have needed to move the y-axis in order to have the same starting point as the sine wave? And for the black, it's there. For the blue, it's over there. And how much of a fraction of a cycle is that in order to have created that shift? Okay, so let's pull it all together. Last part. Let's get a wave moving, time, displacement. There's 2 meters, and we're running on, let's say, 1 second. Then I'm going to show another one, which goes from here. Let's see if I can draw this. Okay. This is tricky. Okay, and that's going between 1 and -1, -2. So let's find a general expression for each of these waves. So y is a sine omega t minus phi. What's happening with the black wave? Right, so first of all, the time period is going to be 1 second. Omega is going to be what's a total number of radians gone through in the time period? Because it's 2 pi. The red, however, the time period is equal to half, or 0.5 of a second. Omega is going to be the total number of radians gone through divided by the time period. It can be 4 pi. I suppose we call this radians per second. What about the amplitude? Is going to be 2, and the amplitude here is going to be 1. What's the shift required in order to make this look like the original sine wave? Well, I need to go to that point there in order to make it look like the original. And that point there is a shift of a total of the red of 3/4 of the time period. So if we're shifting to the right by 3/4, that's going to be a negative shift. Therefore, it's going to be minus 3/4 of a full circle, which is minus 3 pi over 2. So, therefore, if that is my general form, the first one is going to be 2 sine 2 pi t. And the red one will be y equals 1 sine 4 pi t minus 3 pi over 2. If you want to, you could even just get rid of the 1, factorise out pi 4t minus 3 over 2. Good. So this is the general form of a travelling wave. Hope that all makes sense.